Hey, physics, how's it going? So we're going to do our solutions to our magnetic unit pretest here. I'm going to try to make this a little bit faster than the last solutions to the pretest. This one's not as math heavy, it's more just hand rules than anything else. So here we got a diagram that shows the magnetic field at point P. Okay, I really don't know if it really matters about point P. And a current carrying wire oriented perpendicular to the magnetic field, and the direction of the electron flow is indicated there. So you can see that's into the page. So we're going to use our hand rules here because the question one here just asks us, what is the direction, the force that the current carrying wire experiences is. So I'm going to use my left hand rule. Just imagine that this is my piece of paper. Right? So I'm going to use my left hand to do this one. So I'm going to go into the page. Let me just clarify something here. Oh yeah, it's going to go that way. All right. So I'm going to go into the page. So I'm going to go thumb into the page. My fingers are going to be going from north to south. So my fingers are like the arrows of the external magnetic field. They're going that direction. So you notice when I did that into the page, my hand is getting forced downwards there. So I could see that this is going to be towards the bottom of the page. Just put my cursor in the right spot. So just by using my hand rule, kind of hard to show that in a static picture here, but you would have to have some kind of like weird left hand picture here. Not very good at drawing your left hand. So my electron flow is going this way, my magnetic field is going this way. You can see my palm of my hand. So this is the back of my hand here. The palm of my hand is facing downwards. Okay. An alpha particle here, traveling in a circular path, which is good, it has a radius of 20 centimeters. Determine the speed of the alpha particle. Okay, it doesn't say velocity, because remember in a previous video, which I just talked about, speed doesn't change because the force is always going to be perpendicular to the direction. It's always going to be in towards center, while the speed is tangential to the circle that's going. So the alpha particle, couple of key things about the alpha particle that we know. We got the 6.65 times 10 to the negative 27 kilograms. We have the charge of alpha particle, which is 2 e's, which is 3.2 times 10 to the negative 19 coulombs. What else do we have in here? We got a magnetic field strength, and Tesla's there, so that's the B value. Don't necessarily know which direction it is, but we're just trying to find speed anyway. And we know the radius. I'm just going to change that to meters right away. Okay, determine the speed. So when this is going around in circles, we have to determine what forces causing this to go around in circles. In this case, we know that when an object is moving in a circle in a magnetic field, that's going to be my magnetic force. And a force that acts towards the center as this particle moves around, anything that acts towards the center we can label as the centripetal force. So these two magnitudes have to be the same. So to calculate the magnetic force, we go QVB. The reason we use that formula is because it's a free moving particle. It's not a wire or anything. We only use the ILB formula if it's a length of wire. In this case, it's the moving charge. We're trying to find the speed anyway, so there's the V in that formula. And centripetal force is M times A. It's AC because it's centripetal force, centripetal acceleration here. So that's going to be M times V squared over R. So I'm going to slightly rearrange this. You can see that the M, or sorry, not the M's, one of the V's will cancel out with that V up there. So that allows me to have the V by itself on this side. I'm going to times the R up over to this side. I'm going to divide the mass down to the other side there. So we got QBR over M. Okay. Looking pretty good. So just pull out your calculator here. And type it all in. Suppose you don't make a mistake. It should be okay. Just want to double check. my formula sheet here if I got my alpha particle mass right. Yeah, I did. Okay. Boop. So the speed of this alpha particle has to be 72,180. So 7.2. I got 2 sig digs up there. Usually try to keep things as 3 sig digs, but let's just go 2 sig digs on this one. That's 10 to the 4 meters per second. There you go. That's pretty good. The circular path of the perpendicularly charged, or sorry, path of a charged particle perpendicular through a uniform is deflected due to an unbalanced force. If it was balanced, then it wouldn't be deflected, right? If it's balanced out, it just move in a straight line. So it has to be undeflected. So I'm going to cross off C and D because they both say they have to be balanced. Since it's moving in a circular motion, all right, charged particle passing through a magnetic field, goes in a circular motion, as the same thing as the previous question. It's going to be unbalanced. Now, unbalanced doesn't mean it's accelerating or changing its speed. Speed stays the same, but the direction is always changing. All right, we talked about that in the previous video. Okay. Okay, so we're going to use our hand rule here to help us determine the field. So I'm going to put my hand here. Now, the electrons come out of the negative side here. So if you ever get stuck with which way the electrons are going, you can draw a little arrow here. So my electrons are flowing this way. So they're flowing up the front and then down the back. So that's the direction my electrons are flowing here. So that's the direction my electrons flow. That's the direction my hand has to go. I don't necessarily have a picture of this. I guess I could use this, right? So my hand is going to go, let me just double check some with my fingers here. Yeah, okay. So my hand is going to go up the front and then down the back. Up the front, you notice my thumb here is pointed off to this side. So that side is where the north of this magnet is. And that means the other side is the south. Okay. Now, we indicated where the north and the south are, so that's good. There's the north and the south. And then we're going to draw our magnetic field lines. So I'm going to pick a different color here. They come out of the north, into the south, and they will continue moving through the magnet, right? And complete the loop. So out of the north, into the south, and complete the loop. Out of the north, into the south, and complete the loop. There you go. So that's what that should look like. Okay. A current carrying wire is placed in an external magnetic field. Okay. They give us the magnetic field strength, 5 times 10 to the negative 2 Teslas. The current, so I'm just going to write some of this stuff down in our givens. So we know the magnetic field strength is 5 times 10 to the negative 2 Teslas. Oh, that's a horrible day. Okay. We know the current, so that's my I. So 2.25 amperes. So that doesn't have to be changed, which is good. We know the experience of the magnetic force of 3.9 times 10 to the negative 3. Okay, sounds pretty good. Then it just says determine the length of wire. No, not too bad. So we got I, L, B. There's a bunch of other things like we got absolute values. So you got perpendicular symbols here. Let's just assume, oh yeah, it says here it's perpendicular. So everything here is perpendicular to each other. So I'll just rearrange this to get length by itself. There you go. Punch in your calculator. So I get 0.0347. Yep, 3 sig dig sounds good, meters. I'm just going to change that into centimeters, just to make it look nicer. So 3 point, that's supposed to be meters there. 3.47 centimeters. I'm good. Okay, so I really like this question here. There's a question on that electrostatics test. A lot of you, well, not a lot of you missed, but some of you did. We keep on ignoring gravity. Right? Gravity is just too small when it comes to subatomic particles, things that have times 10 to the negative 31. Well, gravity is always there. If you have mass, you have gravity. Sometimes it's just really small and we can ignore it. It's negligible, but it's always there, right? So an electron, even though it has a mass of times 10 to the negative 31 kilograms, it's still producing gravitational field, right? Because it's charged, it's producing a magnetic field, or electric field, sorry. And if it's moving, it could produce a magnetic field as well, because a moving charge produces a magnetic field, okay? So electron properties listed above that can give one of these fields is that, okay, the mass gives gravitational field. It's a really small gravitational field, but it gives one. A constant electric field would be its charge, right? Like I was saying before. And as long as that charge is moving, so that's why these have to be put together. I have a charge and 3 is speed. As long as it's moving, I can have a magnetic field. Yeah. Cool. Let's go to application of Lenz's law here. So a magnet is now dropping into this solenoid. So I have this little solenoid, a magnet is dropping into it. Lenz's law says that there's going to be a current in the coil to try to oppose that. So this is going to become an electromagnet. If a north is coming down to this, the top becomes the north side of my electromagnet. Okay, use red here. So this becomes the north side. This becomes the south. Now I can go down here and just mention, okay, if that's my north on the top, that means my field lines have to be coming out of the north. So I can go down here and say, well, B looks wrong and D looks wrong because my field lines are going into the north there according to these little arrows here. That little arrow is going this way. That's going into the north. That's wrong. All right, so they have to be coming out of the north. That's what these little arrows are doing here. They're coming out of the north. Same thing with C. So it's either A or C, but you can look at A or C and look at the current flow. That's going to be a hand wrapping around this. So you're going to use your left hand. Okay. You got your thumb in the north here, and your fingers, as long as you're using your left hand, your fingers are going to wrap around, and they're going to tell you the direction the current is flowing in that wire. So look at that. It's going across the front this direction, and then around the back. Okay? So it looks like C would be our answer. Yeah. Okay, so we have a proton here traveling through this parallel plate system. It has an external magnetic field as well. It's in there somewhere. I'm not too worried about which direction that is, but the key here is that it's passing through undeflected. So when this proton enters into this field, it's going to be attracted downwards towards that negative plate. So there's an electric force downwards. But to remain undeflected, there must be another force balancing it out. So that's what we're looking for. We're looking for that magnetic force kind of pulling that thing back up. So let's go through. So we want to go undeflected. So that means my FE is going to be equal to my FM. It's a free moving particle, so I can go QVB for that FM side. Oh, we're looking for B here. They give us the speed. Okay, so that's the B. So we're looking for B. Question mark there. Little question mark there. FE, there's only one formula for FE. Talk about parallel plate system here. There are multiple formulas for FE. You can see at the top there's the KQQ, but we can only use that for point charges. So we want to use the E formula, FE over Q. So I'm going to rearrange that. So you got electric field times Q. Then you notice here, this is kind of fun, the charge just cancels out. That's useful. charges cancel out. So that means I have E is equal to V times B. I rearrange this for B. Okay, so it's going to be my electric field divided by my speed. So I didn't need to know anything about this proton other than how fast it's going and what the electric field is. Which is good because those are the two numbers I have here. So I got 50,000 for my electric field. This 5 times 10 to the 4. I'm going to put that number right there. Newtons per coulomb. And then I have the speed of this. I got 290,000 meters per second. Okay. Let's just divide those two numbers. So I got a magnetic field of 0.172. Hey, that's a very familiar number. Cool. 0.172 Teslas. Oh, 2 sig digs, because that's what the question is. There you go. Okay, so now the next question to ask is, what's the direction have to be to maintain this this undeflected motion? So I need that force to be upwards. Okay, so first thing, this is a proton, so it's positively charged. I got to use my right hand. My particle is moving this direction, so it's going to go that direction. Right? Force is upwards. So if I were to draw this on a piece of paper, let's just use my to-do list here. So I'm going to go this way. Force is upwards. You can see that my fingers are going into the page here. Yeah. So they're going to go into the page. So that's the magnetic field. My force is, so try that again. Thumb in. Force is upwards, and then just where my fingers happen to be pointing is the direction the magnetic field has to be to make sure that happens. So that's into the page. Okay, last one here. Oh, key word I see here right away is suspended. So something's got to balance out with another force here. Undeflected, suspended. In this case, it's a wire being suspended. So wire here has a mass of 2 grams. So there's got to be a force of gravity pulling this wire down. To maintain this, there's got to be something pulling it back up. So that means that my Fg has to be equal to my Fm, the magnitude of these two forces. They're obviously opposite directions, so I can't say the vectors are the same. So I can go mass times gravity to get the force of gravity on the wire. Because there's a wire, I can use ILB to calculate the Fm. You may want to change some things, like the mass here, you may want to change to be that many kilograms divided by 1,000. You may want to change the length of the wire to be that many meters. The magnetic field strength looks pretty good, 1.5 Teslas looks pretty good. Gravity we know is 9.81 newtons per kilogram. I didn't say meters per second. Remember, it's not really accelerating. It's suspended, so we can't really say it's accelerating at 9.81. Anyway. Remember, the units are the same, though. What are we trying to find? Determine the minimum current. So we're looking for I in this case. So I'm going to rearrange this equation. Divide the L and the B over. Looks pretty good. Just punch some numbers in my calculator now. Actually, yeah, punch some numbers. I was going to write them out, but why bother? Current has to be 2 sig digs again, 4.4 amperes. Remember, current is measured in amperes, coulombs per second. It's actually, if you want to think of more exact answer, 4.36 amperes. My 3 sig dig answer, but because we want 2 sig digs. My current is 4.4 amperes. There you go. Looking pretty good. Hopefully you guys did pretty well on that one. Remember the next, the test has already been released, so hopefully you've looked through this, you checked out your answers, and you got 3 days to try to finish off this chapter exam here. Okay, I'll see you in a bit. Bye.